a nonlinear dimensionality reduction method for the visualization of high-dimensional data in low dimensions. But why dimensionality reduction is so important? High-dimensional data can cause serious problems, such as overfitting or violating the feature independence assumption in some algorithm. Dimensionality reduction techniques include feature elimination, which is prone to loss of information, feature selection, in which it ranks features based on scores. This method is also prone to loss of information. And feature extraction, in which new features are combinations of old features, so there is less loss of information. T-SNE stands for T-distributed stochastic neighbor embedding. T-SNE is used for the low-dimensional visualization of the high-dimensional data. It is mostly used in fields such as image processing, NLP or natural language processing, genomic data processing, and speech processing. T-SNE starts by calculating a conditional probability between all pairs of points in high dimensions. This conditional probability shows the similarity between 2 points, such that point A would choose point B as its neighbor if the probability is high when we have a Gaussian distribution centered at point A. Then the similarity will be computed for each pair of the points in the lower dimensions based on the t-distribution. The points in the lower dimensions move such that the similarity matrix in both dimensions, the high and the low dimensions, would be the same. Consider mapping a two-dimensional data into one dimension such that the clusters would be preserved. Mostly, this projection cannot be easily achieved by projecting on the axis. In these figures, you can see that if we simply project the points on the two axes, the x and y axis, the clusters would be overlapped. Thus, in T-SNE, we would be looking for a projection in which the clusters would not have any overlap. For each point x of I, we must find the similarity of that point to the other points x of j based on the Gaussian distribution. Consider each point is placed at the center of the Gaussian probability density and find the similarity of the points according to the Gaussian distribution. These formulas show the conditional probabilities in which n is the number of the samples. Then we put the probability values in the matrix. Next step is forming the similarity matrix for all pairs of points according to the conditional probabilities. On the diagonal, the values are 0. The colored part show the similarity estimate. There is high similarity among points that are close to each other. The white part shows small similarity. These points should not be in the same cluster after dimensionality reduction. The points in the low dimensions should be arranged such that their similarity matrix is the same as the similarity matrix of the high dimensions. The probability density that is used for the low dimensions is the t-distribution. In order to find the similarity matrix close to the previous one in high dimensions, we must minimize the Kullback-Leibler divergence of the two distributions using the gradient descent. The figure shows the comparison between the Gaussian distribution and the t-distribution.